Hello, my name is Sebastian. I'm a graduate student at the AVS laboratory, and today I'm going to be presenting on the analytical investigation of two vehicle active charge control for experimental validation. This is ongoing work, and this is a conceptual presentation where I look into the opportunities that we have to do two vehicle active charge control in the lab, why we want to do it, and how we're going to approach this problem in an experimental project in the future. To give you a bit of a background, we're looking into this because we would like to work on the problem of space debris. So, what counts as space debris? Well, that includes a lot of non-functional human-made elements orbiting Earth. That can be dead satellites, rocket fragments, and basically anything that's defunct and that we cannot control that is up in space. So there's this Kessler put out this hypothesis in the 1980s that we will at some point with more and more space debris being created in orbit, we will have a collisional cascade that will render complete orbits unusable at some point. This hasn't happened so far, and he has revised his statement on that, but there's still the risk of this happening in the near future. And looking at natural deorbit times for a lot of objects, they are pretty long for anything below 400 kilometers. It's only a year, but if you go above 600 kilometers, which is still considered low Earth orbit, it can take up to thousands of years. And if you're in geostationary orbit, nothing will deorbit in and by itself. There's a lot of regulatory framework trying to address this problem. Satellite operators are required, based on this UN convention that's shown on the left, to deorbit their satellites within a couple of years after the end of their lifetime. But obviously, since we're talking about a UN resolution here, it is legally non-binding, so there are basically no consequences if those objects are not deorbited. Yeah. That means if regulatory efforts are not very effective, that especially since a lot of space debris has already been created, this can only mitigate further space debris. We need active space debris removal methods. And the graph on the right shows those different methods. Probably the most common one that's proposed is a contact-based removal method, like a gripper arm that just grabs space debris and removes it from orbit. However, a lot of these technologies, if you try to implement them in practice, are very difficult to implement and pose a lot of technical challenges. And since mechanical systems in space are very hard to service, or in general, if they fail, can create even more space debris, we were interested in contactless removal methods for space debris. And one of them is the electrostatic tractor beam that is marked in red here. There are many other contactless methods, but the work at the AVS laboratory has been mainly focused on the electrostatic tractor. So how does this tractor beam work? To try and put it into simple terms, we have a servicer spacecraft, a spacecraft that we can actively control, and the defunct debris object that we cannot control. And what we're trying to do is create an electrostatic force between these two objects. To do this, we irradiate the debris object with an electron beam. By doing that, we emit negative charges from the servicer spacecraft, and that leads to the servicer spacecraft being charged positively, while irradiating the debris object with negative charge, so electrons in this case. We charge this debris object negatively. And if you have the positive object and the negative object, you will get an electrostatic force from that. So we're basically coupling those two spacecraft together without like any physical coupling. And our studies and previous simulations have shown that by doing that, you can push a multi-ton debris object to a graveyard orbit. This is all assuming geostationary orbit because you need the debris length to be quite long for this method to work. It can push the multi-ton debris object to a graveyard orbit within a few months. As I said, we need to induce like opposite charges on those two objects. And for that, we need active charge control. Because we need to be able to actively control the charge on the spacecraft and the debris object. So we've done a lot of work at the laboratory experimentally to take the first steps in the direction of proving that this electrostatic tractor concept is actually possible and feasible. The test beds shown here have focused on showing that we can use electrostatic forces to detumble an object in this case and just create an attractive or repulsive force between two objects, which was done by Seubert, the figure shown on the right, with the two spheres. The big difference here is, compared to the previously proposed concept, is that we apply those potentials via external power supplies. So this assumes we just apply this potential externally. We know exactly what those potentials are, and we just show that we can use electrostatic forces to achieve the things that we claim that we can achieve. For example, stop an object from tumbling, or just create an attractive or repulsive force. So now the next step is going to be that we develop the ability to control those charges without just using a power supply and externally applying the voltage, because that's not very realistic in space. And for that, we have developed a test bed at our laboratory, which is our vacuum chamber, called the Eclipse chamber. And it's shown on the left. We have a whole variety of instruments that we can use in the chamber to create a space environment and to do charging experiments, such as an electron gun. And you can see the charge control setup on the lower left with our retarding potential analyzer for the secondary electron method. That's a sensing method that I'll describe later. We also have the target, a VUV lamp to simulate a spacecraft coming out of eclipse, and an X-ray sensor, which is also to measure the charge of an object. On the other side, we also have an ion gun to create a plasma environment or to do wake experiments, which is shown on the lower right corner. So, previous work that has been done at the laboratory has focused on doing charge control for only a single object. So we have an aluminum cube that we're trying to charge. We have an electron gun that fires at that cube, and we measure the potential with the X-ray detector and RPA. I'll talk about the measurement methods in a second. And we try to apply the correct voltage on and current on the electron gun or beam energy in this case, to achieve a certain target potential, and that uses a PD controller, a control mechanism. And the previous work that was also presented at the conference earlier by my colleague shows that we can actually achieve this target potential within a few steps using different gains. So that's the graph shown on the right. But now we would like to go to two object active charge control, because in the real space environment, we are actually emitting from a spacecraft and not from a fixed electron gun connected to a power supply. And the electron gun is obviously grounded in this experiment, and we just focus on one element, the debris object, as the target, in this case, the aluminum cube that we're trying to charge. However, in a real scenario, we would have both the surface or spacecraft that charges positively due to the charge emission, and we're trying to charge the debris object negatively. And we'd like to look at two floating potential objects in the chamber now, so emitting from one object and charging another object, which is shown in the figure here. So this is the proposal for our new vacuum system that we're trying to design, and this just shows all the elements that this vacuum system will have. But for us, the two elements shown in the middle with the red rectangle around them, that's what we're going to focus on. So as a first estimate, I used charging equations, like the standard charging equations, to figure out what kind of potentials we're expecting on these two objects, if we're assuming that they're both floating, and just how it's going to behave if we reach steady state. So for that, there are very sophisticated methods to do this, but in this case, we just looked at the fundamental charging equations, made a few assumptions, and those assumptions are that we're dealing with a perfect vacuum. We have no plasma effects, so space environmental effects. In these simulations, we use a simple secondary electron yield equation, where the coefficients are given as tabulated values, in this case, coefficients for aluminum. And we use a similar equation that's available for the backscattered electron yield, also for aluminum, since we're radiating an aluminum object. So now we look at the net charging currents, and we integrate them in time until an equilibrium is reached. And Those are the two charging equations that we use for the servicer and the target. They both depend on the potential of the servicer and the potential of the target. So those equations are coupled. And then we just sum up all the currents, and from that we can extract the servicer potential and target potential. So that's what we're solving for. And the coupling specifically is happening when you look at the energy emitted by the electron beam, or sorry, the electron beam current. This current is going to be the current that's applied from the electron gun. However, this can only make it to the target object if the difference in potential between the target object and the servicer is less than the energy that we apply for the electrons. And so that means if the potential difference becomes too large, there will be no net current going to the servicer, and that means we have reached steady state. And now we just look at the results for different prescribed electron beam energies here. We're varying those between 2 kiloelectron volts and 30 kiloelectron volts. That is the range that we can use on our electron gun. And as you can see, we expect the servicer to charge slightly more positive than we expect the target to charge negatively. What should be noted is that typically we do not expect any charging to happen at 2 kiloelectron volts, but that is based on the secondary electron yield and backscattered electron yield, and the equations that we use do not predict this behavior that we see in practice, but those equations are only approximations. And we also varied the currents in the range that the electron gun can apply, and as you can see, the potentials are the same. And since we assume a capacitance, a standard capacitance for the aluminum cube or aluminum sphere, the charging times are absolutely negligible, and the current will only decide how quickly the object charges. But again, we're talking about milliseconds here. So we also have a couple of parameters that we can vary in the model. Very simply speaking, we can vary the fraction of electrons that are emitted in the ion, like from the electron gun, that actually hit the target. We can vary how many secondary electrons return to the servicer spacecraft and how many backscattered electrons return to the servicer spacecraft. And as you can see, the only factor that really makes a difference is if not all electrons hit the target. That can happen if you have massive beam divergence, for example. And that's a practical challenge to minimize beam divergence when we emit from the servicer spacecraft. But with the electron gun, it's not an issue. And the backscattered and secondary electrons, it doesn't really matter. Those currents play basically no role. And also, this all assumes that there are no net electron losses to the wall, which all those chamber effects, if you have a vacuum chamber, there are definitely going to be net current losses and secondaries added from the chamber walls. So this is ignored in this model. Just to go over the experimental design considerations real quick, we're assuming that we're going to have two spheres, conducting spheres of equal size, in this case aluminum. We know from previous experiments that we will need a beam energy of at least 2.5 kiloelectron volts to achieve charging. We need to be right of E2 in the graph on the right. That's from the Shu Li textbook on spacecraft charging, one of the key charging literatures. So yeah, that's important to know. While the simulations don't predict this, this is just known from previous experimental work. Also, the beam current does not really have an effect. We can have a very small beam current and would be still sufficient to charge those objects. It might become an issue if you're talking about massive beam divergence, that you might need a higher current to account for that. And we also ignore coupled capacitance and electric field effects in those initial simulations, so the beam current might actually play more of a role. And especially if you include spacecraft, space environment effects, the beam current does play a role, especially for the charging state of the debris object that's shown on the lower right, part of the slide. This was simulations predict that there is an optimum beam current to achieve a maximum charging potential for this. So yeah, but that is only if you include space environmental effects and not for the simple experiments that we're going to be doing in the chamber. So this is not going to be a factor. And again, object separation is only becoming relevant if you take into account coupled capacitance effects And if you have a large beam divergence, which would lead to, if you increase the distance between the objects, that less electrons are actually going to be hitting that object. So now one of the key questions and the first thing that we will have to design to be able to do this type of charge emission is that we need to emit from the servicer spacecraft, which is in this case a floating potential object. So we need to emit from a floating potential object and cannot just put an electron gun somewhere that's connected to a power supply. So one option is called cathode field emission, but for this to happen, we need a very negatively charged object because this is natural field emission. However, the servicer spacecraft is going to charge positively, so that is not really an option for what we're trying to do. The second idea is to build a simple floating electron, like floating potential electron gun that can be powered by a battery. That will be one of the options that we're going to explore here. And the third option is to use ionic liquid ion sources. Basically, you emit from an ionic liquid, you emit ions, in this case, not electrons. You can emit positively and negatively, which is a huge plus in this case because you can control the charge of the servicer spacecraft in both directions. And I've previously done this work and actually achieved spacecraft charging by using ionic liquid ion sources. But the emission is not very consistent. It's hard to control, and also it is limited in terms of voltage. Typically, I've seen those sources short if you apply more than 2 kilovolts. So it will be difficult to potentially reach enough of a extraction energy for those negatively charged ions to achieve a charging state on the target object. But that's what we're going to be looking into. So now measurement challenges, since we have two floating potential objects, we need to touchlessly measure the potential on both objects. For the negative object, we can use the standard methods we use to estimate the potential of a negatively charged spacecraft, the secondary electron method and the X-ray method, or a combination of both. That's the hybrid method that my colleague J.D. Walker presented on, or has recently published on. And for the positive object, the secondary electron method is unsuitable since it only works for negatively charged objects. The X-ray method might be useful, however, it has been tested for positive charges, and the easiest way would be to use an electrostatic probe, or called track probe, to measure the potential of the positively charged object directly from the object itself. And we can also infer, assuming we have an RPA installed on the servicer spacecraft, which we will have to do at a later step to measure directly from the servicer spacecraft the potential of the target object. If you have that, you can actually infer the charge from the RPA measurement directly. And we actually need to know the positive charging level of the servicer spacecraft to then be able to correctly infer the charge level of the negative spacecraft from the secondary electron method and X-ray spectrum, because they are being changed. Like the measurements will be changed depending on the positive potential of the servicer object. So now again, I've shown this picture before. Key is that we would like to have a horizontal setup in the chamber so we have more space to do this and to decrease wall effects. So if we're just shooting straight at the object, there will be much more space behind it instead of a horizontal setup. And we will have the possibility at a later point to introduce space environment effects like coming out of eclipse by turning on the VUV light, or in general simulate space conditions in the chamber and plasma conditions. And our key research goal for this project is to validate basic predictions from the electrostatic tractor modeling work. So now, what is the experimental plan going to look like in detail? First, we have to set up the external sensing. So the very first thing is that we have to figure out a way how to emit negative charges from the servicer spacecraft, such as building a custom electron gun or using electrospray thrusters, and figure out how the servicer charges based on the emission from that electron source. We need to do this sensing touchlessly, either with a track probe or a secondary electron method or any of the previously mentioned methods. And we also have to figure out how much the beam divergence is so we can figure out how close we have to place the target object. And then we can try to figure out that we place the second object in there as well and try to measure that potential as well. So we have two floating potential objects. There will be no control at this point. So the second step would then be to install the sensing setup on the servicer. Since this is important because if we are in space, we cannot have an external sensing setup. In the chamber, we can just put the secondary and the RPA and the X-ray detector like somewhere else in the chamber. It doesn't have to be on the object itself, and that's easier as a first step. But then we have to actually move it onto the servicer spacecraft and figure out how we can still correctly measure the potential of the target object. And there's no precedent for this. This hasn't been done. And ideally, if we can then emit, charge the other object, and measure the potential from the servicer directly, we can think about closed loop control for this, how we can actually deliberately influence the charges we have on both of these objects to then, which would be needed in the electrostatic tractor to vary the forces that we have between the two objects and like consistently control those forces. And then obviously at some point we'd like to introduce space environment effects because we're dealing with a highly idealized environment in the vacuum chamber for now. I'd like to acknowledge the support of the Air Force Office of Scientific Research, and those are the references that we used. Thank you very much for your attention. I hope this talk was interesting and informative, and hopefully it illustrated some of the work that we're doing at the ABS laboratory. Yeah, and keep looking out for more publications to come on the subject.